Welcome to our video on using counting methods to find probabilities. Basically, we're going to be using the fundamental counting principle to calculate probabilities, and that's just a fancy way of saying using permutations and combinations to figure out the number of good and the number of total. Because remember, probability is good over total, and you just have to count up how many ways you can do it the good way that they're asking you to, and the total way. I'm also going to show you a simpler dash technique that I've invented myself that helps simplify these ideas. So you can either use the formulas or you can use the dash technique. They both work flawlessly. It's just whichever one you prefer. So I'll show you both. All right. Now with typical, what we call classical probability, um, we've seen before how to count up an entire sample space. And once we have an entire sample space, we know the total, right? We know how many total ways something can be done. And then we have to find the good out of that depending on the question. Well, we're going to use the dash technique or permutations and combinations to enable us to kind of more quickly come up with these good and total numbers, especially when the sample space gets rather large. It would be too clunky to list things out by hand. So here's a simple example. Suppose that you are one of 20 students, and they're going to select 3 students and send them off to a conference trip in Cancun. And if all the names are thrown in a hat, right, and they pull 3 out at random, what's the probability that you and your 2 friends, Leonard and Sheldon, all end up being chosen? Okay? Well, first we have to figure out what's the total number of ways we can just choose 3 grad students from amongst 20. And then we have to figure out how many ways can the 3 of you, right, you and your 2 friends, be chosen from that group of 20. Whenever you're doing counting questions, the first question you have to ask yourself is, does order matter or not, right? Is this going to be a combination or a permutation? If order matters, then it's a permutation. If order doesn't matter, it's a combination. And what I mean by order mattering is, imagine doing the choosing and then rearrange the way that choice happened and see if it's a different outcome. So let's say we're going to choose 3 students. We choose you, then Leonard, then Sheldon. Okay, that's one outcome. Now let's take those same 3 people and choose them in a different order. So if I chose them in the order Sheldon, Leonard, and then you, is that a different outcome? Does it change how the experiment happened? And you answer no, because it's the same 3 people going to the conference. So in any order that I choose those 3 people, it doesn't matter. So order doesn't matter. So this is a combination question. An example where order will matter will come up later, but I'll give you a quick one right now. If instead of just sending the 3 of you off to a conference, we were choosing 3 students to be president, vice president, and secretary of, some committee, then if I choose you, then Leonard, then Sheldon, you're now president, right? But if I choose Leonard, then Sheldon, then you're now secretary, and Leonard's now president. Same 3 people, but in a different order gives us a completely different outcome. And in that scenario, that would be a permutation. Order matters, okay? So we're in a combination situation because order doesn't matter. So we would use the combination formula in our calculators, or if you don't have a calculator, do it for you. It's a pretty easy formula to do it, right? It's n choose r, where n is the number of things you have and r is how many of them you're choosing. And it's just n factorial over r factorial, and then the difference, n minus r factorial. And the beautiful thing about factorials is they cancel, because this is going to be 17, 16, 15, all the way down to 1, and the 17, 16, 15, those will all cancel. And so you're really just left with 20, 19, 18 over 3, 2, 1, which reduces to 11, 40. That's the number of ways that we can just choose 3 students to go on this trip. That's the total. Now we got to figure out the good. How many ways can we choose these 3 people we're talking about, you, Leonard, and Sheldon? Well, there's only one way, right? Because if you rearrange those 3 people, it's the same 3 people. So it ends up being 1 out of that 1140. Okay, that's the beauty of probability, is that it gets really simple if you just boil it down to the simple parts. My dash technique makes it even simpler because we're choosing 3 people, right? How many ways can we choose those 3 people? Well, we've got 20, then 19, then 18, because we can't choose the same person twice. And because order doesn't matter, we have to count up the number of ways we chose. And if you multiply these together, you see that you get the exact same 1140 that we did before. All right. If order did matter, you wouldn't put anything in the bottom of those dashes. And that's the dash technique for just doing simple counting. But the great thing about the dash technique is not only does it help you count up number of ways, but it also helps you do probability. So you can kind of do it in one step rather than multiple steps, right? So instead of counting up how many total there are, 1140, and then figuring out how many ways we can just choose the three of you, being one, we can use the dash technique and do it all at once. So if it's a probability question, you still treat it the same way. You ask yourself, okay, how many things do I have to do? Well, in this case, I have to choose three people. So you always put down the number of dashes you have for the number of things you have to do. Three choices of three people, three dashes. Okay, remember, probability is good over total. So all you have to do is fill in each blank with the good and the total. Okay, the, the probability is, right, that you and your two friends are chosen. So how many good choices do you have for that first person to go to Cancun? And hopefully you're all saying three, because there's three choices. It's either you, Leonard, or Sheldon. Out of how many total choices? Well, 20, because there's 20 total students to choose from. All right, now I've chosen one. There's only two good choices left, right? Because if I chose, let's say, Leonard, now I only have you or Sheldon to choose from, and there's only 19 total students, and then there's one out of 18. And when you reduce this, right, these will all reduce down, you'll end up getting 1 over 1140. You get the probability. You don't have to do two steps. That's the beauty of the dash technique, is you can get the answers directly rather than having to do a combination and another combination and then do a fraction of those two combinations. All right, let's look at an example where it's going to be a permutation. Order matters. So let's change the previous example just slightly. And suppose that as being one of the 20 graduate students in that physics department, you have a chance of being selected for one of the three student spots to go to Cancun. The names of all the students are put in a hat, three are drawn. However, if your name is drawn first, you get all expenses paid. If you're chosen second, everything is paid for except meals. And if you're chosen third, you must pay for your own meals and hotel. So do you see how now order matters in how you're drawn, because you're each getting a different thing, right? You're no longer all three just going to the conference under equal footing. Depending on the order in which your name is drawn, you're getting more or less stuff paid for. So now when you think, okay, do a draw, do yourself, Leonard, and then Sheldon. Now rearrange those same three items and go Sheldon, Leonard, and yourself, and you can see that that's a new outcome, because now Sheldon gets everything paid for and you don't, whereas in the first example, you got everything paid for and Sheldon didn't, right? So order matters, so it becomes a permutation. Okay, well, how do we calculate permutations? Well, that's 20p3. Still, a 20 is our n, 3 is still our r, but now the formula is just n factorial over the difference factorial. See, the only difference is we don't have that little r factorial on the bottom. That's the only difference between those two formulas. The 17 factorials still cancel, and then you're left with just 20, 19, 18, and you no longer have that 3, 2, 1. So now you get 6840. Now, let's consider how many outcomes are in the event that you, Sheldon, and Leonard are chosen. Well, remember, order matters. So there's all these different ways where you could get picked along with your two friends, depending on how the order works, right? These are all different orderings of the same three people. Now remember, this question also changed in that they didn't want to know what's the probability that the three of you get chosen. They wanted to know a slightly more specific question is, was the probability that you and your two friends all end up being chosen and that your name is drawn first? So if we go back to all of these different ways that the three of you could be chosen, we have to make sure that we only pick the ones where your name is drawn first, and there's only two of them. So you would put 2 over 6840 and get that answer. Now, it seems like that would be a big pain in the butt to list all those out and then figure out how many of them, right, have you going first. Well, that's where the dash technique comes to the rescue again, because we don't have to do this, we just have to do the dash technique. How many things are we choosing? Again, 3. Okay, with this specific question, you have to be picked first. So how many good choices do we have for that first person? Just one, just you, out of 20 total people, right? Okay, now the second person can be either of your two friends, either Sheldon or Leonard. So don't you have 2 choices for those two out of 19? And then now you only have 1 choice left and 18, because once you choose one of your friends, there's only 1 friend less left. And look what you get. You get 2 over that same number that we saw before, and we get the exact same answer. The dash technique makes things so much simpler. All right. The complement of an event, sometimes denoted by E with a C, but actually more widely denoted. Many textbooks actually do this, E with just a horizontal line over it for the complement. Sometimes they do like a hat, and sometimes they do a little tick mark. But this seems to be the most popular, most common in textbooks. You don't see this one a lot, but our particular book does do that. But just know that there are many different ways, unfortunately, that they can denote complement. Whichever symbols they use, just know that the complement means everything in your sample space that is not in E. So think about it in a real simple case. If you know what a deck of cards looks like, right? You've got ace through 10 and then jack, queen, king, and you've got that in 4 different suits. And if you talk about the event E being drawing a card that is a face card, then you have jack, queen, king, 3 of them, times 4 suits. That has 12 out of 52 cards. Well, the complement of E would be all cards that are not face cards, right? And those would be the other 40 out of 52, right? Because if you have 12 that are in your event, then the rest, 52 minus 12, 40, are in the complement. It's just that simple. It's the other side of the coin, so to speak. And oftentimes complements are not the same size as the other thing, right? So I try not to use the whole head tail thing, because then people think it's 50-50. But a complement is just anything that is not in your event. So let's see if we can describe the complement of these things. If you roll an even number on a die, what would the complement be? Well, wouldn't that obviously be all the odd numbered things, right? If you choose a number that does not end in 1 from all positive 2-digit whole numbers, well, basically, isn't that just going to be all numbers that end in 0 or 2 through 9, right? Any number other than 1. And then from a class of 52 students, choosing a student who is over 21 years old, the complement would be anybody who's 21 or younger, because they said over 21, right? So if someone was 21 years old, they wouldn't satisfy that event, but if they were 21, they would satisfy the complement. So like I said, the first one was odd numbers. The second one would be all numbers that don't end in 1. So basically everything except for 11, 21, blah, 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 blah. And then the complement is 21 years old or younger. Like we said, right? 21 years satisfies the complement because the actual event had to be older than 21. All right, here's your first skill check. Go ahead and pause the video and see if you can do these. Kind of a tricky one, because it said which of the following outcomes could be in the complement of the event. So these aren't describing a complete complement, they're just describing things that could be in the complement. So if you had some difficulty understanding why it was all the above, it's because they were kind of tricking you by saying in the complement and not just the complement, right? So these are just pieces of things that could possibly be in the complement rather than the entire complement itself. Well, once we understand what the complement is, we get 3 very simple kind of rules, almost identities, that should be kind of a no-duh thing, right? Because if E and E complement are the 2 sides of the coin, right? They're 2 pieces that come together to make the entire sample space, then obviously the probability of one plus the probability of the other has to equal 1 because now you've accounted for the entire sample space. And then the other two is just some simple math, right? Just move this to the other side and you get 1 minus p of the complement, or move the other one to the other side and you get 1 minus p of e. So it's basically just saying the probability of an event plus the probability of its complement always adds up to 1 because the event and its complement end up giving you all possible things in the entire sample space. And we know the probability of an entire sample space always has to add to 1. How about another example using some nuts that were imported into the United States between 2006 and 2011? So here's our data, right? First one, what's the probability that the walnuts you consumed during this period were from Austria? Well, go back here. If we want to figure out the probability that the nuts you had were from Austria, then we're basically just trying to figure out how many Austrian nuts there were out of all nuts, right? It's that simple. So we're just picking one thing. We only need one dash. And remember, we're not looking at all nuts. We're just looking at walnuts. So we're really only concerned with the top half of the chart. And yes, I know there's more than one walnut, but we're looking at them as one group. So that's why we only have one dash. And in that one dash, if those walnuts came from Austria, we get that as the good. That's how many total, what is it, pounds? Pounds, yep, weight in pounds. And then it would be that over the total. To get the total, you would have to add all of these together. Because again, we're only looking at the walnuts, so we're not looking at the ones below there. And that number, whatever it is, I'm not going to waste time doing it right now. That number would go here as your total. And it's that simple. Right? So we know it's 1938. We know the total. If you add all those together, like I said, 18508, put those two together, and there's your probability. That simple. Okay, what about the second one? Probably the walnuts were from somewhere other than Austria. Well, if this many were from Austria and this was my total, then wouldn't not from Austria basically be the complement? It'd be 1 minus this, or if you just took 18508, subtracted 1938 from it, that would be all the others, right? And then that's what we get. You could also just do 1 minus the probability that we found to do that if you were okay with having your answer as a decimal, which is something we should talk about here really quickly. Is you'll notice that in all of these answers that we've seen, we had a fraction and then we had these little squiggly equal signs and a decimal, because all of these decimals have been approximations because we've had to round, we've had to stop because the decimal kept going on and on and on, and so we had to stop it at some point. When in doubt, when you're asked for an answer, always leave it as a fraction before a decimal. And in fact, you want it to be a reduced fraction. So you should take 1938 over 15508 and reduce that as far as it will reduce. They're obviously both even, so you can keep dividing it by 2 and do, most fancy calculators, if you put that in and then do an equals and then go math fraction thing, it'll bring it back to a reduced fraction. And that's a better answer than 0.104711, blah, 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 blah. Wherever you round it, you're rounding. So it's always not perfectly 100% accurate. So that's why we want to do fractions if we can. So I would only suggest doing it this way if you were asked to give an answer and it said, round your answer to 4 decimals or something like that. Then you've got enough decimals here that you can now take this and you can round it to 4 now and have 8953. But if it wanted a precise answer, then you would have to go back and use the actual fractions and do 18508, subtract 1938 from it, get that number, and put that number over 18508. Okay, so it just depends on if they're asking, for precise or rounded is okay. And then the last one, assume that you also purchased pistachios during this time period. What's probably the pistachios came from somewhere other than Italy and Sweden? Well, if we go up here, pistachios is the lower half. We want somewhere other than Italy and Sweden. Well, we don't have Sweden in our list, right? Well, that would be a problem, except they asked for Italy or Switzerland, and I'm just a moron and said Sweden, right? So Italy or Switzerland is fine. So we go back here, and we just would have to take out Italy and Switzerland. So if you take these two numbers out, then that's the good, whatever's left over, right? Pistachio. So these three and this one, add those together, that's going to be your good. And then put them all together, right? Everything is the total. All of this is the total. So again, simple, 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 one dash, put the numbers in there, and you're good to go. So Italy and Switzerland, right, over the total. Again, the better thing would be to reduce this down and leave it as a fraction, unless they tell you specifically to answer, round your answer to 4 decimals or 3 decimals or something like that. And then if you had to find not from Italy or Switzerland, it's going to be 1 minus that number or 1 minus that fraction. Okay, guys, so complements can sometimes save us a lot of time and energy. The most common use of a complement you'll see later on is whenever you get an at least question. So whenever they ask for the probability of at least one, blah, 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 it's always easier to do 1 minus the complement because the complement of at least one is none. And it's a lot easier to calculate the probability of none of something than at least one, because then you'd have to do one of it happening plus 2 plus 3, depending on how many there are, all the way out to 7, 8, 9, whatever it is. So the complement's always going to be easier in that case. All right, that's it for this time.